Hey guys. All right, topic 3.3. Topic 5.3. Bond enthalpy. All right, this is actually a very interesting topic. We took a look at 5.1 based on colorimeter. How to get thermodynamic answers, data, results from doing an experiment by looking at the difference in temperature. That was fun. Hopefully you enjoyed the lab. 5.2, we talked about Hess's law. How some reactions are so hard to do that we have to break it up into intermediates and find out their individual delta H's and add them up. Okay, we looked at the heat of formation. That was neat by looking at data that are already discovered, for us. We looked at the combustion data of various combustible elements. Now, those are great. Those are pretty accurate. Then we're going to come across, of course, this thing called 5.3 known as bond enthalpy. Looking at how much energy does it need to break a certain bond and how much energy would you get when forming a new bond. Because if you spent more in breaking than forming, it's going to be endothermic. It's like an investment. You invest more money than making money, you're going to have a net loss. That's unfortunate. So nature doesn't like that. Remember I mentioned before, nature favors exothermic, meaning you want to be the other way around. You want to spend less energy breaking bonds, more energy getting from making bond. Like in business, you want to spend less of an investment, but you want more in a reward, which means your net will be a gain. Man, that sounds great. But that's what bond enthalpy, that's what this section is all about. Okay, and hey, remember we learned about Lewis diagrams, those Lewis structure with octet rule? That comes to play today. Okay, that's when you should know how to draw these things because now those things are important. So let's take a look at how this works. So we're talking about a chemical reaction here. Okay, for any chemical reaction, let me just show you a chemical reaction, a simple chemical reaction. H2 plus O2 will give you H2O. Now you're going to have to balance this or else this whole thing makes no sense. Now if you were going to draw this, you're looking at two H's sharing a bond. You have two set of these. You have oxygen, double bond, another oxygen. Don't forget those lone pairs. I've been forgetting about them lately. That will make 2 mole of water. Okay? Now, in reality, how does that work? Well, you need energy. First of all, this is like a business. You need to invest some money before you make money, assuming net-wise you're making money and not losing. So first, what you need to do is you're going to have to spend some money. You're going to have to spend some energy. And this energy is spent on breaking bonds. So you're going to break these H bonds. So let me just erase. So you're going to have to break these bonds. Okay, you're not making ions though. That's one thing you're not doing. You're not making ions. What you're doing is you are breaking the connection between H and H. Kick your electron back to where it came from. Same idea here. Okay, you're breaking the double bond. Breaking the double bond. Okay, so how much energy did you invest on breaking this, breaking a pair of those? And now what you're going to do is that you're going to be making new bond. And this new bond involves taking two H and an O together. By having the O say bond with one of the H and bond with the other H to make one of these. For this guy, same thing. Bond with one of the H, bond with the other H, and make one of these. When you make bonds, when you put together something, and if this something is stable, it will release lots of energy. We mentioned that before. When a chemical is stable, it is more in terms of exothermic by number. It will be a higher negative value for delta H. We mentioned that last class. Okay? So here's your investment, breaking the bond. And here's your reward, making those bonds. If these are stable, they will have a large negative delta H. Hopefully, this delta H is bigger than these combined. So you get an XO. If not, you get an endo. No problem. Just a different types of reaction. The reaction will be cold, whereas the other one will be hot. That's the idea here with bond enthalpy. Okay? Bond enthalpy is exactly that. Okay? So, one more thing. Okay, one more thing. Just before we move on to the next page. You notice that we broke this bond, okay, between H and H. Broke this bond. So let's say to break that bond, you need, I don't know, 50 kilojoules. Okay, let's just say it's not, okay? It's not. It's 50 kilojoules to break this bond. How much would it be to form this bond? Now that's pretty simple. We've done something like this before in Hess's law. Remember Hess's law, one of the rules is that if you flip the reaction, reversing the reaction, you reverse the sign. So if it takes 50 joules to break this bond, it takes 50 kilojoules to make this bond between two H's. Something to keep in mind, okay? So to make this bond, invest 50 kilojoules. To break H and H. If you're making H and H, you're going to get negative 50 kilojoules. Negative 50 kilojoule of energy release by making that bond. We'll put all of these things in a mathematical formula later. And we'll do some math. Something that you guys love to do. All right. Bond enthalpy. Okay, the whole idea here is the energy required to break 1 mole of bond in a gaseous covalent molecule under standard conditions. So we're always looking at standard condition because how do we know how much energy is it that bonds contain? Well, somebody have already done that for you, but that somebody did this in the state of standard state, 1 atmospheric pressure and 25 degrees Celsius. Okay, and I'll show you in the next page where that information is from. But that's what bond enthalpy means. Oh my gosh. So if delta H is positive, that's an endothermic process, and we all know that. Okay, also known as, of course, bond dissociation enthalpy, because you're trying to break bonds. Break bonds. That's why, of course, the delta H is positive, because you're breaking bonds. And of course, these values, okay, are right here. Okay. In terms of the IB booklet, this is, going the other way, 11. Okay, so section 11 in your IB booklet tells you the amount of energy a bond needs to needs to break, and how much would you get by forming. So if you look at this, it's pretty simple to read. Let's say you are looking at this bond right here, BR. Okay, BR2. You're looking at this bond right here. How much energy do you need to break this? On average. Notice I said average here. Oh my goodness, it's very important that you mention the word average. Is 193 kilojoules. So it takes 193 kilojoules to break this. Obviously, it takes 190. You will get 193 kilojoules when you make this. Average is the key word. Average is the key word. Why is that the key word? Well, let's just say you have this. And you're going to break the OH bond. When you break the OH bond, let's say you break this one. You break this one. So it becomes OH. You get that. You know how much energy you have to invest to do that? You need to invest 502 kilojoules to do that. To break that bond. Now, that's an OH bond that you broke. Man, that's an OH bond that you broke. And you're going to do the same. You're going to break this OH bond too. Because you want all of these to be little individual atoms when you put them back together. But the thing is this, though. The thing is this. To break the second OH bond, it's not 502. It's actually easier. It's actually 427 kilojoules to break the second OH bond. So this right here, this number, where's OH? This number right here, that's actually an average of all the OH bond that there is to break. It's not just these. There's other chemicals with OH in it. Like, for example, alcohol, like methanol. You want to break this? It's not going to be 502. It's not going to be 427. It's going to be something else. But that's part of the OH bond breaking party. So these number are average number of all the OH bond that can be broken. So what that means is that this unit, 5.3, the number that you get, is going to be inaccurate. Yeah, but good enough. Hopefully you understand that. Okay, hopefully what I just said there, you guys can kind of picture it. So if you were to do, find a delta H using formation like we did the other day, and you find the same delta H by doing bond dissociation, and you look at the two number and you're saying, how come these two numbers are different? What's more accurate? What's more real? Who's lying to me? Well, just to let you know right now that these numbers that you're going to be using, they're not that accurate because they're averages of all types of the same bond, but under different molecular structure. All right, let's continue. Okay, so bond enthalpy can be affected by these things. Okay, how much energy it takes to break this bond versus that bond is based on a couple of things. Bond length, right? Bond length, we talked about that before a long time ago. Okay, basically the longer the bond, the weaker the bond. Okay? I think we even did playing with molecular structure and even proved that. Bond types, the type of bond. What kind of bond are you talking about? Are the two bonds polar? Non-polar? Ionic? Covalent? Hydrogen? course, bond polarity. Same thing. Okay? These are all things that can contribute to the amount of energy that is required to break the bond. So let's talk about bond length. Kind of talked about this before. Okay, when we were looking at trends. Man, that was a long time ago. As bond length increases, bond strength decreases. So if I were to ask you a question that I asked you before, a long time ago, under these three, what they all have in common is that they all have hydrogen, but what's different about them is the halogens that they're bonded to. Right? Looking at their radius to radius, which one is the shortest? Which one is the longest? Well, iodine, okay, is the biggest here. Oh man, iodine is huge. So from radius to radius, oh, this is going to be long, man. Fluorine is small. Oh, fluorine is tiny. So when you have radius to radius, that radius is going to be short. So when you think about this, the bond between HF is definitely stronger than the bonds between HI. Longer? Weak. Shorter? Strong. Good thing comes in small package, huh? So HF will have a larger bond enthalpy, meaning that the energy that you will need to break, it's going to be a lot more than the energy to break. You know what I mean. Nice to know these atomic radius back in the days, isn't it? It can be used to explain a lot of things. All right, bond types, as in like single bond, double bond, triple bond. I think that's what I was going to say. I think I might have said something else earlier. But as you can see, double bond it takes more energy to break a double bond than a single bond. Okay? Now, those of you who are biologists, that might not be true all the time. That might not be true all the time. Because there are these guys called enzymes, okay, that may be able to recognize CC double bond better than CC single bond. And by breaking the double bond, it might actually take less energy if you have an enzyme. An example is unsaturated fatty acids can be broken down easier than saturated fatty acids, where unsaturated fatty acids has carbon-carbon double bond. But that's if you have an enzyme. We're not talking about no enzymatic reaction here. We're just talking about the amount of energy needed physically to break these things. But of course, double bond is stronger theoretically than single bond. With no biology in mind. Biology. All right. Polarity. Okay. How polar something is dependent on the difference in their electronegativity. We talked about that before. Basically, the higher delta En, the more polar something is. So HF being more polar than HCl, bond enthalpy is higher because you have more polarity. There's more polar involved, which makes the bond a little bit stronger. Okay? And hence, these guys are smaller too because the radius. That's another contributing factor. All right, let's do some math. This is the part where you've been waiting for. Let's calculate delta H based on bond enthalpy. I have a reaction right here. Okay, I have a reaction right here. Why did I say it's probably a good idea that you know how to draw these things? Because you have to know. C2H4 looks like this. You have one C double bond, or one CC double bond, and 4 CH bonds. So you have one CC double bond and 4 of these CH bonds. You might want to write that down. So 1 CC double bond, 4 CH bond, and then we'll find what the numbers for these later. HBr is H bonded to Br. So you have one HBr bond. And that looks like a 4 there. Okay, and we'll look up what that number is. All right, it's probably a good idea that you know that C2H5Br looks like this. So CH3CH2Br. This reaction has a name. Okay, we'll talk about that when we do organic chemistry. Can't wait for that, huh? No, now look. Okay, count all the type of bonds. There's a CBr bond. There is a CC bond. CC single bond, that is. And there is a whole bunch of CH bond. Let's count how many CH bond. There's 1, there's 2, there's 3, there's 4, there's 5. Ooh, there's 5 CH bonds. So, let's summarize. In order for the reaction to occur, all these bonds must break. This bond will have to break. Everybody has to break. And then you reconnect them back together into this structure. We want to know the energy that you get from making these bonds, is it higher than the energy that is used to break these bonds? Hope I said make these bonds to break these bonds. If it is, it's exothermic. Nature's favor that. If not, it's endothermic. By applying this equation right here and look up these values. So let's look up these values. Let's take a look at what is CC double bond. CC double bond is 614. So this is 614 kilojoules per mole. Now, mole is very important. Okay, mole is definitely important, but it's not a big deal here because you're taking everything into account. Okay, so if anything, let's just say if there's 2 of these, you just have to make sure you multiply whatever the total is by 2. We'll see. We'll see. Okay. Oh, what else? CH bonds. Oh, that's a popular one. So how much are CH bonds? Well, let's look it up. Okay. CH bonds, so C and H. So that's 414. Man, we're going to have to use that number a whole lot. So CH bond is 414. Here, there's another one right here, 414. Let's take a look at HBr bond. This one, because there's one of them. HBr, HBr. That's 366. So that's 366. Just blow that up so you guys can see. All right, CBr. CBR. Right here, 285. CC bond. CC bond is right here and here. Okay, 3, 4, 6. So 3, 4, 6. Okay, we got all the numbers. Now we're ready to solve this. So let me have my big open bracket. Okay, there's how many bonds broken? Well, there's a CC double bond broken, and that's worth 614 kilojoules. Plus, there's 4 of these CH bond broken. So that's 414 kilojoules. There is an HBr bond broken. That's 366. Well, let me put this here too, so that way you know there's only one. Okay. So as I said, remember, if there's a 2 here, you're going to have to make sure this is 2, 8, and 2. Just a reminder, because you'll come across a question like this in the next page, which I want you to do for homework. All right. Let's close this bracket. Minus. Okay, let's sum up all the bonds being made. So there's one CBr bond, and CBr bond is worth 285. Plus, there's one CC bond, and that's worth 346. And finally, there is 5 CH bond that is worth 414. Done. Close your bracket. You put this junk into your calculator, and whoa. You actually get 65 kilojoules per mole. Okay? That's what you're going to get. Of course, you're basing on per mole of C2H4 or per mole of HBr. Okay? Or you can say per mole of this being made too. Okay, so every one of these that you're making, you're going to get 65 kilojoule worth of energy. Hey, and it's exothermic, so this reaction is definitely favoring nature. How does that sound? As I said, if you were to do this question again, using enthalpy of formation instead, which you can, you'll notice that you might not get the same answer, but it'll be close. The reason? These numbers are all average of all of these bond types. And remember, all of these guys can have an effect on those bond enthalpy. All right? Hopefully that sounds good to you and you understand exactly how this works. If you do, guess what? Do this one. Okay? I know. This one is a big one. This one is huge. So try your very best to accomplish that by finding out what is delta H R by looking at the bonds, all the bonds here. Okay? Here it's all O2 bonds. Okay, it's a whole bunch of these. 25.2, so there's 25.2 times of these because there's one double bond. You get the idea. Okay? Here, there's 2 CO double bond, and there's 8 of them, so in total there's 16 of these C double bond O bond. You get the idea. Okay? Now, I want you to find what the answers is. At the same time, if I were to look at the combustion of octane, remember this page? These are all the combustion delta H. If I look for octane, which is right here, octane is 5,470. Is this going to give me something close to that? If it is, bond enthalpy is a good way to illustrate the energy for this. If it's very, very different, I can tell you right now, this one is more trustworthy, way more trustworthy. Because the difference in value is stated right here. Why don't you find out and let me know? All right. To finish off, okay, I have just a couple of things to say. The reason for the difference, of course, so this kind of answer your question here. This actually answer this question that your answer right here is not going to be this number, not even close. Now, why is there a difference? Well, there's 2 assumptions that you can make. Okay, first of all, when things are in gaseous state, there's no intermolecular force for gases. So a lot of these polarity stuff doesn't come into play as much as before. Okay? And again, average values. Okay? Average values. Anyway, do that question. Hopefully you understand this bit. And then we're actually done with topic 5, and we're going to move on to something that's a good continuation for topic 5, which comes in the form of topic 6 on related rates. All right, bye guys.